there again, today's lecture, I got as far as FA and then I got distracted. Of course, it's on Faraday's law today. So let's start off with Faraday's. We had this in the last lecture, but it's worth just recapping. So the integral form of Faraday's law, that's the one we're going to use today. We're coming back to the differential form and we'll be concentrating on that. The differential form of the Maxwell equations almost entirely from Friday onwards, but we're going to look today at the integral form of Faraday's law. And remember, the line integral of the electric field round any, again, sorry, it's difficult to see, to make the scalar product here a bit bigger, is equal to, round any closed path, gamma is equal to the, well, first of all, I'll take the negative rate of change outside. As I mentioned last time, we can take the time derivative inside or outside the integral over space. It's the integral of the negative rate of change of the normal component of the magnetic field over any surface S bounded by the loop gamma. So let's make this 8-1 so we can refer to it today. I mean, we've already used this equation. And then this is, if you like, the original form. Sorry, this is probably a bit low for the, I hope everyone can see, I'll write it a bit higher up here, is minus d phi b by dt. And this, of course, is the same equation. And I said last time, Faraday, amazing experimentalist and made incredible range of discoveries, discovered the law in this form that the EMF induced was the negative rate of change of the magnetic flux. It was then realized by Maxwell that what we mean by an EMF is precisely this line integral. So if you like, this is almost an abbreviation for this side. And likewise, when one's done a bit of vector calculus, one can recognize that the magnetic flux is precisely this normal component of the magnetic field integrated over the surface. So if you like, we could regard this side as an abbreviation for this side. So those are the equations that we're actually going to use today. And just to remind you that, we'll be ploughing on, particularly from Friday onwards, into what I would call the real fundamentals of electromagnetism. But we're going to skate over. I mean, it's incredible variety. We looked at these a little bit in the lecture on Monday, some of this amazing technology and incredible effects that one gets from electromagnetic induction. And, if we were doing an engineering course, we would go on deep into some of these properties. However, we're doing a physics course, so we're going to look at some more abstract and high symmetry, of course, examples of how to apply the law. So the first one that we're going to do is a typical physicist type of problem where we have a very strange circuit. And let's imagine that we've got a circuit in which, so this is the circuit, this is metal, this is just a metal circuit, and this is also metal, this end part here. This is also metal and it makes a circuit, but this is supposed to be a movable crossbar. So in other words, we're sliding one piece of metal across the circuit and we slide it at some velocity v. Now, what the dots represent is that we've got a magnetic field coming up through the plane of the view graph. So in other words, we have got a static magnetic field, a B field, and we have got it in this sense. Now again, the point of this geometry, if VO45 has got any chalk, oh yes, a little stubby bit left over. So example 1, we're going to consider 3 examples of, today. Example 1, let's say the flux changes because the circuit is moved. In this case, perhaps part of the circuit is moved. So again, we've got now, we choose this very high symmetry problem. Of course, the normal, we want to consider the loop gamma will be precisely what is represented there by the red and green line. That's a loop, that's what the actual circuit consists of. And first of all, well, what is the magnetic flux through the surface? Well, it's our usual sort of approximations to make things easy on ourselves. The normal component to this surface is also directly vertical to the plane of the view graph. So B dot n is just the magnitude of B. The angle between these is 0, and so magnitude of B, magnitude of n times the cosine of the angle between them is just the magnitude of B. And of course, again, the physicist type of approximation, we've got a lovely huge region of uniform magnetic field. So all the way around this loop gamma, through this surface S, the magnetic field is uniform. So the B also comes outside the integral. So the surface integral just becomes the magnitude of B times the integral of the area. Well, it's a rectangle, so the area is precisely the width of the circuit times its length. So this whole calculation is with reference to figure 36 of the course handout, and we can say that our phi b, our abbreviation from the magnetic flux, is clearly equal to the constant magnetic field B times the length times the width. All we've got to do is multiply this constant magnetic field by the area occupied by the loop. So again, this is such a simple problem that we can just go straight to the EMF. Again, the magnitude of the EMF, come to the sign in a minute. The magnitude of the EMF is clearly the negative, well, if we're just doing magnitude, the rate of change of B, L, W. And again, we've set ourselves up with an extremely simple problem because B isn't changing as a function of time. You know, we've just got some enormous permanent magnet giving us a lovely, clean, homogeneous magnetic field. The width of the circuit is not changing as a function of time. As I move this crossbar across here, the width of the circuit is constant, but L, of course, is changing as a function of time. You know, a little bit later, the crossbar has got to here, and this length has precisely increased as a function of time. So this is immediately equal to d, we can take the B out front, the W, dl by dt. But dl by dt, the way the length is changing as a function of time, is just the velocity v that's written on the view graph. So we get that the magnitude of the EMF is the magnitude of the field times the width of the circuit times the velocity with which we kick the crossbar across the circuit. Of course, you know, we wouldn't make a practical circuit in this way. This would be it's sort of set up as a physicsy example. Now, I'll come back to some of the coursework that's been set. If you like, that bit is the first bit of the coursework. You'll then ask the stuff I'm going to set this Friday on Faraday's law. You'll then asked to go on and do some further calculations, and you're asked to calculate the current. Well, first of all, if we've got V equals IR, if we've got the voltage drop, let's say the circuit has got a large resistance, of course we get a current flowing. And the current is given in this way. Again, I don't know if you, excuse me, it's gone all a bit, that is the magnitude of the force on the crossbar. It's the width times the current times B. I'm not treating that in this course. Apparently that's now taught at schools as Bill. I said, you know, has anyone heard of this? And somebody said, oh yeah, that's Bill. Bill? No, his name's not Bill. What's that? And, oh, it's the length times the magnetic field times the current, written B-I-L. Anyway, we won't deal too much. You can derive Bill now, if you like, from the Lorentz force on any individual electron and use our relation between current density and I to derive that for yourself. Now, Of course, this gives a retarding force. I know the current, I know Bill, which in this case is Wib, and so of course I get the force. Now, you'll notice I've put a minus sign in here, and that is because of conservation of energy. Now, this is the important point about the negative sign in Faraday's law, and this is why this sort of silly kind of circuit is used as an illustration, because this will clearly, when I gave the all I'd have to do is give the crossbar an initial flick. Let's see, it's a physicist crossbar, it's frictionless, so it just slides across. Well, if as a result of that, the force came out in this direction, it would accelerate forever. All I'd have to do to solve the world's energy problems would be to take one little circuit, give a crossbar a flick, and hey, of course I could use this current I'm getting to, light my light bulbs, run my factories, computers, offices, and all the time the crossbar would be getting faster and faster, and I'd be drawing off more current. So the force has to be a retarding force. This force here has to retard the crossbar and pull it back this way. And if you didn't have the minus sign in Faraday's law, you would break conservation of energy. So it's not just put in there, it's the negative rate of change of flux. So in other words, and this is what, when people say, oh, the EMF tries to oppose the flux change, it's a bit anthropomorphic. If we try and increase the magnetic flux through the circuit by making this crossbar move out here, the EMF that's induced produces a current which produces a force which tries to make the magnetic flux, tries in inverted commas, to make the magnetic flux less. In other words, the induced EMF opposes the flux change. So that's a very, very important point. Just to bear in mind too, we'll come back, there's a whole lecture later in the course called Electromechanical Implications of Faraday's Law, and so we will be revisiting this, but note that the retarding force is velocity dependent, and again, we did this in year 1 maths, this is like a friction. It's not a mechanical friction caused by this crossbar sliding over here, it's an effective friction, and I mentioned that last time when we were looking at the eddy currents in a pendulum, a view graph which is now, of course, in traditional style, escaped me, but I will hopefully find amongst my view graphs as things go on. So we've got now a retarding, there it is, lurking furtively. And it's a similar thing here. I mentioned this, that it's a weird effect if you actually see it. If you swing a great big plate into an electromagnet, as it enters the field, it's like it's hit this pot of honey. It's not touching anything, but you see a frictional force retarding its motion. There's a more advanced bit on the question I'm going to set on this, which is what happens if the rod and the whole circuit of figure 36 were made of a superconductor. And I gave a big hint on that by telling you what would happen to the pendulum. Because remember, these currents will always exist. It's just a matter of if you've got no resistance to dissipate the energy, what will they do? So that's something to think about. So we get a velocity dependent, i.e. frictional, effectively frictional retarding force. And I'll underline the retarding force. Note that if there is no negative sign in Faraday's law, excuse me, this is my usual problem in working in this lecture theatre is the the lack of board space. So I'll have to continue on this side. This is just writing it up because it is an important point. We would contravene conservation of energy. So this negative sign is not a kind of like little arbitrary add-on. And indeed, it's so important, it's got its own name in physics. It's called Lenz's law, which is that the flux, the induced EMF opposes the flux change. So in other words, or alternatively, of course, if we tried to kick the crossbar this way and decrease the area of the circuit, the flux change would be the other way. It would be trying to increase the flux change. So that's fairly obvious. Now, talking of energy brings us on to certainly the most important practical calculation of the course. Say we've got some more important fundamental ones to do, but we're going to now do the maths of the AC generator. So again, because of knowing I was working in here, I'm going to go through this step by step on the view graph rather than on the blackboard. So at its basic level, an AC generator is simply a coil of wire rotating in a constant magnetic field. That's all it is. I say all it is. We're very glad that this is the phenomenon that works. So now again, we now have to be a bit more careful, because let's say, for the sake of argument now, the magnetic field is just coming across the lecture theatre, enormous north pole, enormous south pole, and some straight field lines. Well, obviously, when the coil is like this to the field, we've got a maximum flux, which is just like in the last example, the area of the coil times the field. But when we have it in this sense, there's no flux going through it at all. And of course, in this case, B dot n, we really do have to consider is now equal to the magnitude of the field. Remember, the magnitude of the field itself is not changing as a function of time. This is just a constant, steady magnetic field coming across the lecture theatre. What's changing is the angle of the coil with respect to the field. So we really do have to say that the B dot n part of this is B cos theta. And then, if we multiply by the area of the coil, we get the magnetic flux through the coil. So in this case, our right-hand side of Faraday's law, we've got to take the time derivative in a minute, is BA cos theta, where theta is the angle between, so here's the surface normal to the coil, that's what's changing as a function of time. The coil, we're mechanically spinning, so this is B cos theta, this scalar product, and then we integrate over the coil, we get BA cos theta. But now let's say, and this is precisely what we do technologically, that we spin the coil just at a constant angular velocity. In fact, we know perfectly well that we have got 100 pi radians a second is what's going on at Selby. We know that in British AC mains, the absolute frequency is 50 hertz. It's 60 hertz in the States, it's 50 hertz in Europe. So this is just 100 pi, radians per second. So we spin the coil at a constant angular frequency, well then the angle is omega t, where omega is the angular frequency, basically the definition of angular frequency. So now our magnetic flux is the B times A times the cosine of omega t. Now, of course, again, it's the same thing. We've worked out the magnetic flux. We want to know the rate of change of magnetic flux. So the rate of change of magnetic flux is going to be differentiating this expression with respect to t. Now, of course, the field itself is constant. The area of the coil is constant. It's just cos omega t, which is time varying. And of course, if we differentiate cos omega t, we get omega sine omega t. Now, having gone to all that trouble of rotating a coil in a field, we wouldn't just put one turn of wire around the coil, we'd put loads. And the same EMF is induced in each turn, so the total EMF will be n times the d phi by dt. And that's what's done in the next two stages of the calculation. I'm sorry about this, like you can see that, with the blackboard space, I try and go through this if you want to make notes as we go along quite slowly, so that it sort of corresponds to, more like writing speed. So for a coil of n turns, we have got the same EMF induced in each turn of the coil. Each turn is sharing in the motion, and then d by dt of BA cos omega t. Again, B and A are just constant, come out the front, and d by dt of the cosine of omega t is omega sine omega t. So the total EMF that we get by spinning a coil in a magnetic field is the number of turns times the magnetic field strength times the area of the coil times the angular frequency, and then sinusoidally varying as a function of time, and this omega will of course depend on how rapidly we're spinning the coil. So when you get into the engineering side of science, you just say, well, my generator is just producing a sinusoidally varying EMF of this type. And so we lump all of these symbols together into epsilon naught. So it's a very simple idea, but we do quite like having power stations and electricity, and this is what is producing it. And about 20 kilometres south of here, there is an absolutely huge magnet rotating next to an absolutely massive coil, and that is sending electricity. And I just plug in here, and hey, it works. But remember that this is often just treated as a voltage. We often use the root mean square EMF that power stations produce, which is simply 240 volts in this country. We have step up, step down transformers. There's more to it than just a direct connection, but effectively this is what's happening. And in a sense, the final answer is intuitively obvious. If you want a big EMF, you have lots of turns, you have a massive great magnetic field, you have a coil with a huge area, and you spin it as fast as is technologically possible. How many people have been? Yes? Well, I have simply, basically all that I'm saying there is that I am producing an EMF which is going in this sense, and it's got some amplitude, epsilon naught, and all that I've done is I've condensed these figures into a single symbol. So the EMF that I'm actually getting is time varying. Now, what's coming out of the socket here is a time-varying effective voltage, come to that in a minute, of magnitude epsilon naught. Has that answered it?
I was confused because I thought you were in the permittivity of free space epsilon naught.
Oh, thank you. Yeah, no, this isn't the permittivity. This is a capital epsilon naught. The permittivity of free space is a little epsilon naught. And I usually write the permittivity of free space. You can write it with this sort of like that style or that style. Of course, I'm, like most lecturers, not consistent, and I vary randomly between the two. But so, yes, thank you. No, I see. No, this has got nothing to do with the permittivity of free space. This is simply the magnitude of the EMF that I'm producing. So my turn to ask you a question. How many people have been to a power station? Only a few. It's an amazing sight. I once went to... Cue rambling anecdote. I once went to a power station in North Wales, which was hydroelectric power station, and I went at about 11 on a Sunday morning, and it was all very quiet. Oh, this is pretty boring. It's huge. It was like the size of St Paul's Cathedral inside a mountain. And this power station works. They've got a lake at about 800 metres and a lake at about 200 metres, and 6 rather large tubes which lead down from one to the other. And one of the things that hadn't occurred to me was, well, I've just gone, it's all very quiet, but suddenly at about 11 on a Sunday, all the people, not all, that's cultural prejudice, a lot of people in Manchester and Liverpool put on a Sunday roast. And suddenly the grid needs a lot of energy. And they just open these 6 pipes. And I can tell you, I was as far away from one of these I'll come to it in a minute. You can either rotate, of course we know from relativity, you can either rotate the magnet or rotate the coil. And I was about as far away as I am from the window there, and you could feel the wind of this magnet rotating. This thing is like massive, huge piece of iron, and it starts rotating at 100 pi radians a second, and you can actually feel, and you actually get the impression of what it's like when a city starts to use a lot of electricity. It's a truly amazing sight. And of course, there are various huge power consumption oscillations in Britain. And the guy in the control room showed us, oh yeah, it happens every Sunday, this. He says, but that's not the biggest spike of consumption that we get. And he showed like this huge spike of consumption at about 8:30 in one evening the previous summer. 8:30, what happened then? You can tell this is a long time ago because England had actually got to the knockout stages of the World Cup. And 28 million people were watching. I think it was England play Belgium in the last 16 or something. And at half time, everybody, again, cultural prejudice, a lot of people go out to make a cup of tea. You just saw this huge spike of in fact, Norwich Power Station has got an overall negative energy output. It's precisely used as a storage power station. What they do is that when electricity is cheap in the middle of the night, they use the electricity to pump all the water up to the upper lake, so that when they need it, they can release the energy back down. So they store it actually as gravitational potential energy by pumping the water up. And then when the grid needs to cope with a power surge, like it does at half-time in a World Cup match or Sunday lunchtime, back it comes. So this is, of course, massive technology, literally massive. Again, I won't say too much about the technological aspects, but I did include some figures in the course handout because this is so important. We've done it in the simplest possible geometry, a coil just rotating in a uniform field. Of course, if you rotate the coil in practice, you don't want it all to get tangled up. So you need various things like slip rings and so on, so that when you rotate the coil next to this enormous magnet, and like the magnet, which is weighing tons, misses the coil by a fraction of a centimetre. You don't want to waste any of the flux. It's amazing technology. And these wires, they're sketched there, they're like as thick as your wrist. They're huge, great, more like rods of copper. It's amazing technology. But you can, this is sort of the calculation that we did, is shown in figure 39, where the coil rotates next to a magnet, slightly more complex geometry, but the same idea. And then later on, and this is the point with the epsilon naught, the engineers treat this whole thing in here like it's a black box. And outside, we have an effective voltage. Now, between A and B, we've got an effective voltage drop. We've got an epsilon is equal to an epsilon naught, a capital epsilon naught, sine omega t. We just abstract from all this. This is the real stuff that's going on that we know how to calculate as physicists. But in the end, it effectively produces a voltage. Because, we're 20 miles away, excuse the non-SI unit, or so 15, 20 miles away from Selby. We don't experience directly the changing magnetic field. We take some wires, some great rods of copper, and we draw off an effective voltage. But again, to mention, although this is an effective voltage, we can't describe it as the gradient of a potential, strictly speaking. Yeah. So, of course, technologically, actually, here again, you can imagine you're going to lose quite a lot from friction. In order to have actual slip rings that connect your copper rods to something that's rotating, you've got to have an actual real connection at this point and this point. So it's not often it's often done by, and this is the kind of power station I saw, you rotate an enormous magnet next to a fixed coil. But again, you get the same kind of maths. You have a black box and you get a voltage drop between points A and B. So technologically, we've done a very easy calculation, the usual thing, but technologically you'd normally spin the magnet next to the coil. And then finally, in this little series of view graphs, we really make the abstraction for engineering of just saying, oh, well, there's something going on in a box and it's giving me this voltage drop. So this is and then we, that's when now we go to engineering, we have a little circuit. Oh, now the sum of the voltage drops across the resistor and the capacitor and inductor must be a constant. And we do, if you like, electronics. And, we like electronics too. Electronics is all, we quite like having computers and radios and televisions, etc., etc. Let's not knock electronics. But in electronics, that's all there is to it. We just abstract everything to just be a little symbol. So that's the electronics. And just to mention again, as one of my many feeble kinds of jokes, but nevertheless, in this case, a true one, it's rather ironic that from this course we can now understand the generator, but you'd need kind of 18 lectures in the chemistry department to understand when you put your bike battery in what's going on. That is utterly beyond us. Because that's matter. That's a property of matter that is, and like I don't know. Did you do this at school where you have a lemon and you put a bit of zinc in one end and a bit of copper in the other, and you can light a tiny little lamp from it? And that is actually really complicated. The AC generator, by comparison, is very straightforward. So there's a lot, of course, of technology that we skip past. I'm now going to set you a paradox. So I should say, board notes, example 2. You might have taken notes as you went along, but please, if you've not done so, of course this is up on the VLE notes, the AC generator, and let's say see figure 38, and that we went through it, epsilon is epsilon naught, not little epsilon naught, thanks for that, sine omega t, where the magnitude of the EMF that we produced is N, B, A. Omega with the symbols as follows: number of turns in the coil, constant field, constant magnetic field, area of coil, and angular frequency of coil. So, as I say, Faraday's law we're going to come back to later in the course, in particular when we study the energy topic. I mean, obviously this is massively important for energy. And indeed, you could say the major problem facing your generation technologically is that you could sum up in just having a look there at going back to view graph 40, is to keep these enormous magnets spinning without increasing global warming or various types of pollution. I mean, nobody wants the magnets to stop spinning. I quite like it when I come home and the thermostat has switched on the central heating, nice bit of technology, and then it's already dark at 6 in the evening, it's pitch black, and I just go click, and all the lights come on, and you think, oh, now I'm warm and well lit, and this is something we don't want to give up. But of course, at the moment, we mainly burn fossil fuels to boil water, drive the steam through turbines, and that creates, as the steam passes through the turbine, the massive rotational power that drives the coil. But at the moment, we've either got to think, well, we're going to have to do with less of these, or we're going to have to find some very clever way to keep them all spinning that doesn't make a mess of our planet, which would be a bit of a shame, really, wouldn't it? Yeah. Only got the one. Except if you believe the many worlds interpretation of quantum mechanics, and then we've got loads. But You know what I mean? So here's a brain teaser for you. So my third example, I'm going to leave as a completely open question. And indeed, that's something you might want to discuss like in your tutorials next week. Big plug for the problem classes and tutorials. You know, 22 out of 30 of my students at my class yesterday. This kind of stuff, again, you can't learn it passively. You've got to practice the calculations, and I hope you take advantage of the tutorials. So first of all, again, it's set up deliberately in a slightly funny way. We've got some charged metal spheres. So on all of these spheres, there's an equal charge, let's call it plus Q for the sake of argument. Yeah. So we've got some charged spheres, and they're not. There's no conducting circuit here. They've been embedded. They're all separately embedded in a plastic disc, and the disc has been mounted on a spindle, which is very, very finely balanced. Yeah. So we've got this whole thing is mounted on a spindle, which is quite finely balanced. Now, we've got a current I flowing through a solenoid, yeah? And so, and this, you know, to emphasise that this has got nothing to do with we might not know what's inside a battery, but we know it's producing a constant direct voltage, and therefore it's producing a constant current, yeah? Now, we know that inside that solenoid there's a magnetic field. We did this derivation. The magnetic field is the number of turns per unit length times, well, mu naught, of course, times the current. Yeah. And now, by some accident, let's say the engineer who has put this funny device together has made a bit of a loose connection with the battery. And don't get fooled, the answer to this problem has got nothing to do with this like asymmetric position of the battery. You've got to put it somewhere, so to speak, but it's on the disk, you know, it's just there. And this connection just breaks. Now, we haven't touched the device from the outside at all. We haven't touched it. It's been set up and then just left. But the wire comes loose, or indeed the battery runs down. And when the battery runs down, well, or the wire's broken, I becomes a function of time. We get a di by dt. Now again, to emphasise that this is not a trick question at all, we could also have simply dispensed with the battery altogether and made the coil out of a superconducting material and set the thing up below Tc. I was asked some questions yesterday. What is the difference between a perfect conductor and a superconductor? And if you've got resistance as a function of temperature, a perfect conductor would do that. A superconductor does that at some particular Tc. So this will be the superconductor. And again, I'm sorry, I know I got some good questions at the end last time, but you need to go a bit further into statistical mechanics and solid-state physics to find out how the superconductor works. Very roughly, you decouple the electron system from the phonon bath, and it's a collective phenomena. The electrons form what are called Cooper pairs, after one of the three scientists, Bardeen, Cooper and Schrieffer, who developed the early theory of superconductivity. And they behave, although they're fermions, they spin half particles, they behave like effective bosons, and so they stop seeing the lattice, they stop being scattered, and so suddenly there's no resistance to the electron flow. That's deep in properties of materials, but we could, without knowing that, we could certainly say, well, I know that that's a Tc, and let's say, for the sake of example, it's somewhere around liquid nitrogen temperature. We've set this up at liquid nitrogen temperature, and then again, without touching it from the outside, we just let it warm up. Well, as it goes through Tc, suddenly the current would have been flowing forever, but if we keep it below Tc, but at Tc, suddenly the electrons experience resistance and the current drops. So we could have arranged for this current to drop in a different way than a loose battery lead. It would be the same problem. But now we do get into a problem, and we get into the paradox. For whatever reason we get a di by dt, well then certainly this doesn't stay constant because the current's changing. We get a dB by dt. Yeah? And if we get a dB by dt, by Faraday's law, we clearly get a non-zero line integral. If I now go round this loop, sort of running out of colours here, I've got a blue pen somewhere. If I now go round this loop, there is a non-zero line integral because I've changed the magnetic field. Remember, the magnetic field, this is a solenoid, its field lines, that's, you know, north-south, its field lines are going like that. And if so this is now equal to the negative rate of change of the normal component integrated over the area. Well, now certainly the normal component of my magnetic field has changed as a function of time. We don't have to calculate it exactly. We know that there's magnetic field lines that are normal to this loop gamma as I go around here, because the magnetic field lines are coming in this sense. So we've changed the normal component without any detailed calculation. We've got a non-zero line integral of the electric field going round here. But we also know, remember, we're not doing much on the Lorentz force in this course because you did quite a lot on that in EM1. Oops, excuse me, cross product, not add. And here, well, let's just concentrate on the well-known, the force is the charge times the electric field. Well, on each of these balls has definitely got a charge, and they're now in a circulating electric field. So all that we're saying from our analysis using Faraday's law boils down to saying each of these charges will feel a tangential force going around the disk. But you know, they're bits of metal embedded in some plastic, so they should start now to make the disk spin. And you think, okay, yeah, that all sounded very convincing, Martin. I now come, well, you may think that wasn't very convincing, but you can see there seems to be a very strong argument that without having touched this disk at all from the outside, I can make it spin. And you think, wait a minute, there's a pretty fundamental principle lurking out there, the principle of conservation of angular momentum. I haven't touched this disk, and now by some electrical effect, it starts to spin. So I've not conserved the angular momentum of the system. That's a pretty deep principle, conservation of angular momentum. And it seems to contradict this Faraday law analysis of the situation. So I'm not going to give you the answer. I will later in the course. You know, I won't leave you in suspense forever, and you may well find that you could discuss it with your tutors next week when we have EMO tutorials. And so I'll leave the question to you: will the disk rotate if the current I is stopped? It seems to be a contradiction between two. I've told you the Maxwell equations are always true. And we've just applied the integral form of one of the Maxwell equations and come to one conclusion. And somebody from the department would say, no, wait a minute, in order to make something spin, you've got to apply a torque to it. You cannot, without touching a system, simply, if this just warms up through TC, I haven't applied any torque to it, have I? I've not touched the system from the outside. So anyway, there was a little example 3. Example 2 was the AC generator. Example 3, a paradox. And I won't make board notes on this, there's no space to do it. And the paradox, what I've just done in words there is outlined on the VLE note. So let's just say see figure 37. That's what we've had a look at. So talking of questions and paradoxes and so on, I've got a few minutes left at the end, and I don't want to start on charge conservation now. I want that to be a completely separate lecture. I've mentioned to you that we've got to this sort of stage. We're coming back to this. So we'll be coming back to the differential form, and today was the last time, in a sense, when probably, you know, the theoretical physicists and mathematical physicists, oh, thank God all that practical stuff's over. But we're getting on to some slightly more mathsy stuff on Friday and next week. We've got to this stage where now we've studied this governs electrostatics when this happens to be naught. We now actually have the complete field equations for the electric field. We've looked at that. That's, if you like, Gauss's flux law of electrostatics. This is Faraday's law. We know there are no magnetic monopoles, and we have this last equation, and we know that there's a missing piece because, you know, we're looking back from over a century and a half. Now, Maxwell realised that this law couldn't be correct. And he realised, and it's not obvious, of course, unless you're totally a genius, it's probably not obvious to you that this law contravenes charge conservation. You think, oh no, Faraday's law is a perfectly good law. It's telling us that, you know, I've got, if I have a current density in space, then I have a curl that points along the current density and a line integral of a magnetic field that goes around it. What on earth has that got to do with charge conservation? And well, that's exactly what will be the lecture we do on Friday. So that's where we're going. And of course, once we've got the missing piece and we can study the so-called Ampere-Maxwell law, then we'll be in a position to do the unification theory because we'll have the complete equations for both the electric and the magnetic fields. So that's where we're going. And is it true that Roddy wears different coloured trousers for different levels of difficulty of lectures? Well, and green for an easy lecture, sort of amber for a kind of like intermediate, and red for the tricky ones. Well, I think today this is appropriate. And kind of like pretty rubbish, kind of greeny, beigey, somewhere between green and amber today. Friday and next week I'm coming in my bright red trousers, and you go, oh no, here comes the field equations. We've still got 5 minutes. I'd just like to say something about the problems, because I think a few people, one or two people have struggled with the magnetostatics problems a little this week. So I'm just going to give a couple of clues. And the one that I think's bothered a lot of people is this L-shaped wire, you know, when a current... Oh, excuse me, let me get a view graph pen that works. So the idea... So we get a current, and again, you know, it's typical physicists, you know, problem. We have an L-shaped wire. There it goes, and the current goes in here. And at some point above, we're asked to calculate a magnetic field at point P. Now, I think without the hint, this possibly was a bit too subtle. So here comes the hint. You don't have to use the Biot-Savart law. Of course, you can solve any problem with the Biot-Savart law because it comes from the vector potential, and we could solve it that way, but there's some nasty integrals to do. The idea is that, well, again, this is our power of imagination as physicists. Imagine that this is an infinite wire going this way. Well, if it's an infinite wire, I can certainly solve the situation with Ampere's law. We've done that. And we know, you know, the magnitude of the field is mu, you know, we've done this one to death, mu naught over 2 pi times I over r. Yeah? And we know too, again, we've not studied it, but the right-hand screw rule, you'd have learnt that before, and we know the magnetic field lines circulate. So imagine that the wire is like this, and the magnetic field lines will circulate. So at this point, if the current's going this way, right-hand screw rule, the magnetic field will point towards you, yeah, above the wire, because it's circulating. So at this point, it's coming around this way as like a right-hand screw. So it's in that direction. So this wire is producing a field in that direction. Now, there's, again, a slight subtlety, and you get all the marks anyway, even if you've not got this, because this would be a tricky thing. A semi-infinite, this is real physicsy stuff, a semi-infinite wire does produce half the field of an infinite wire. So the imaginary bit doesn't actually give you a magnetic field, so you actually sneak in a 4π there. But the yeah, I know it's that's cylindrical chickens in a vacuum again. Here we go. Now this wire, so we know what's going on there. Well, this wire is also semi-infinite. Let's pretend it heads off to infinity this way. Well, it's going to produce a field of the same magnitude. It's got the same current going in it, and this distance here from the corner, I think it was called h in the problem, is the same, yeah, the same distance. So we certainly, yeah, at this distance, just have to pop the h in for the distance r from the wire. Again, it produces, but in magnitude, the same field. But now, let's say the wire has done its L shape here and now heads towards me. Well, now the field's circulating that way, so this semi-infinite wire produces a field in that direction. And I've now given you more than enough hint. If you can't add up a vector which has got equal magnitude, it's going like in that direction and that direction, it's clearly going to produce a vector which is diagonally in between them and which has got the magnitude that you can calculate because you know how to add two vectors together. So that one was causing some trouble, and the other one was the Helmholtz coils. Still got a minute or two, so I'd like to just have a quick look at this. I think the first bit of problem 5 was really easy because it was just a recap of what we did in the lecture, in effect, in lecture 6. You know, you just had to calculate the magnetic field on the axis of a circular coil. And you know, because we did it, that is equal to mu naught I halves, and then a squared over a squared plus x squared to the 3 halves. Yeah, we know that, but it's, and the Helmholtz coils, you have the arrangement where the radius of the coils is equal to the separation. And the point, you see, like, it's very easy for me, and all these lectures on steady state, and like today in Faraday's law, I said, oh, we've got a completely homogeneous magnetic field. Well, how do you do that? It's actually quite easy to get a homogeneous electric field. You just get an absolutely whacking great big flat capacitor plate. And you really can make a homogeneous electric field by just making these huge plates, and then the field lines go from the positive to the negative plate, and you really can make a homogeneous electric field very easily. How do you make a homogeneous magnetic field? You know, that's not so straightforward, and this is how, and again, people who say do psychology, for example, I got a lot of complaints from the year 1 mathematicians that I didn't have enough psychology jokes. That was a main complaint about the course, you know, more psychology jokes. And my wife has been saying, don't get fired. Okay, so anyway, the psychology joke is, no, I won't tell it. I better not. No, but I mean, in a way, that, you know, they use all these MRI scanners, and you know, then of course they see somebody doing some task, and this bit of the brain goes ping, and they say, oh look, you know, that's the ping effect in that side of the brain, and look, oh yeah, when somebody's thinking about that, you know, that bit of the brain goes, oh look, they're using language, and that bit goes ping, you know. Well, the real stuff that's in there, it's amazing technology, and part of the technology, you need like a 3 Tesla field that's bigger than a human head to do this, you know, in a massive homogeneous field, and this is basically kind of how it's done. The idea, the field lines are all going in this sense. There's my field lines, yeah, and roughly in this region I want them to be completely homogeneous, yeah. So what I would have to do, if I wanted a really homogeneous field, you've got to consider the field produced by, if you make your origin, say, x is naught here. The field, you can certainly, and you want to calculate the field in the middle at, let's say, x is a halves. Well, of course, the field produced, you know, this isn't an easy problem. You've got to think about it. The field produced by this one at x is a, you've got to shift this along. You've got to shift your x along by a. So if you want to make that coil 1, you make that coil 2, you've got to sub in x minus a here. But the clever thing is, and you'll see this if you do the differentiations, my dB by dx, almost by symmetry, is going to be naught. And again, you'd have got you get the marks even if you don't get this far. But with this arrangement, where of course you've got to take the derivatives and then sub in correctly, also this arrangement gives you d2b by dx squared is naught at the middle. So you've got a field which is, it's not perfectly homogeneous, but is very homogeneous. Actually, its third derivative doesn't disappear. It's not completely homogeneous. But you know at your level, differentiating a squared plus x squared to the minus 3 halves and then subbing in the appropriate value for x is not so hard. But seeing what to do is quite tricky. Okay, I've run slightly over. Look forward to Friday. Bring along, I'll bring my red trousers, you bring your intellectual crampons, and we'll start to climb a bit.